This lecture will be a continuation of the last lecture. I will be not very careful and informal and just explain some ideas, leaving details to my future notes. But so first, I want to explain a bit one thing which I briefly mentioned last time, but I think it is important for today: the relation between story about integral system and L operator, which we mentioned, and Q characters. Let me recall that there is a universal R matrix for the UQ of G hat. And this R matrix has triangular decomposition. Where in this part we have terms like E alpha plus N delta times EF minus alpha plus N delta. And in this part we have terms like E minus alpha plus N delta times F alpha minus N delta. And here I assume that alpha is a positive root. And R0 part corresponds to the loop to the Cartan part of the UQ of G hat. And formula for this, we showed it on the first L2 case, even for L2 I'm meeting some details, but anyway, it will be some very finite part, which corresponds to finite dimensional Cartan, times exponent of the following. Sum of m greater than 0 q to the power m here this Cij tilde I will define in a minute more explicitly, but in words this is inverse to Cartan matrix. Of course, Cartan matrix is now Q Cartan matrix. And HIs are loop generators of the affine quantum group. If you want, if one can write this formula in more short terms, introducing dual basis. So if you say that, say H I tilde M is a sum of a J C G I Q in power M times H J M, then of course this will be just RH exponent Q minus Q inverse sum M over M HIM times HI tilde minus. Just again, so we had this formula before for SL2, this generalization, and let me spend a minute to explain what is this matrix C tilde. So here Cij without tilde is just a Q deformation of the Cartan matrix. AJC. And C of Q and C tilde is the inverse to this Q deformed Cartan matrix. So for example,
and this is a non-affine Cartan matrix.
Non-affine, yes, non-affine. This non-affine, and almost probably almost except first lecture, where I have some hopes, I assume that we are working simply laced case. Let us show you some examples. So, example. Okay, what is it? So SL2. Then C is a matrix where we have just one number 2, and C tilde is a matrix. Okay, this matrix where we have 1/2, or if you want to write this explicitly, this will be 1 Q inverse. Let me skip something and write to SL4. In this case, C is the following matrix: 2, 1, 1, 2, 1, 1, 2. And C tilde, we have a common denominator, which is 1/4. So it is well known that the determinant of the Cartan matrix for Q equal 1, term to the Cartan matrix is the size of the center of the corresponding group, and for SL4 it is 4. And now everything is Q deformed, but this is determined again Q deformed, so we get this, and remaining part will be will have clearer form in terms of Q numbers. So here we have 3. Maybe one I should write Q here. Here we have 3. Here we have 2. Here we have 1. Here we have 2. Here we have 1. Here we have 3 plus 1. So C tilde is a matrix. We have some denominator, and then so up to some simple denominator, we have point matrices, which are quite nice. Maybe okay. Maybe it's okay. For example, maybe this now let me recall that we have that for any fine dimensional representation. So now let V be finite dimensional rep of UQ of G hat. And then let me we have definition of the Q character. This definition looks like this. We decompose V into direct sum of the L weight spaces. L weight spaces, they correspond to the function, they are labeled by the functions phi, each function. So, okay, just set phi 1, phi r, such that for any vector zeta which belongs to subspace V phi psi I plus minus on zeta is equal to phi I of Z zeta. And these functions phi are quite special. They have the form of phi of z is equal to some power L, and then we have a ratio of the rational functions. Greenfield rational function. This R of z is Greenfield rational function. For highest weight, it is a polynomial, so Greenfield polynomial. But for other vectors, they're just rational functions of the form, say, product of z minus as or product of z minus bs. Whereas, no, such. And this, I will also use the definition of this formula in terms of the Heisenberg, namely the corresponding formula is that M's mod of the I's Heisenberg acting on zeta is equal to q in power minus m. So we have now number and summation of the as in power m minus summation of bs in power m zeta. So after these preparations, we can recall the definition of the Q character. So Q character of V, it is a sum of the dimension of the corresponding subspace times product of over I, then product of as yi of as, then product of as yi of bs inverse. Here for shortness I omit the region of the product, but of course I do not impose that number of a's and number of b's are equal. For example, for highest weight vector, this function r is polynomial, so we don't have b's, and we have some set of a's, and actually the cardinality of the set is just highest weight with respect to the constant descent. Okay, this is. Are there any questions? Okay, if there are no questions, so let me just move further. Okay, I think you see my screen, everything should be okay. So let us recall that last time we defined the transfer matrix LV, which is a rho V tensor identity applied. Change color. Applied to universal matrix and transfer matrix TV, which is trace of a first subspace of the LV. And if V depends on the sum evaluation parameter, then of course we write LV of U and so on. And I claim that actually this Q character should be viewed as a TV to which we applied Harish-Chandra projection. So I assume that it was not said very clearly, but actually it can be. So I just spent some time to explaining what does it mean. Explanation what does it mean. This TV belongs to UQ of B minus. This is because the universal matrix itself belongs to UQ of B plus, where they put in below maybe, B plus times UQ of B minus. And this subspace UQ of B minus has the following decomposition. This is a I will write decomposition not the whole space, but subspace of zero weight, the weight with respect to constant SL2. So we have weights with respect to constant SL2. In terms of this notation, we just ignore this delta. So elements of the UQ of B minus, they should have the same number of alphas, and sum of the corresponding alphas and minus alpha should be 0. And if we have element of zero weight, there are two possibilities. First of all, it could belong to the subspace. Let me denote it by U imaginary. And so it means that we do not have real roots, F which correspond to real roots. And if no, then it belongs to subspace U plus of minus infinity U, actually this U minuses, because this B minus, U minus of imaginary part, U minus of plus infinity plus 0, where this is generated by F alpha minus n delta. This is generated by F minus alpha plus n delta. And this is generated by F n delta. So either we do not have elements, these Fs which correspond to real roots, or we have, of course, something from F with minuses and F with pluses. And there is a natural projection from here to UQ of to UIM, which just takes the quotient of this subspace. I denote this projection by HQ and state proposition HQ is homomorphism of algebras. So in other words, it means that this subspace is actually an ideal. And this should be called as Harish-Chandra homomorphism. So the QL. So we work in two different situations and also loop situation. The proof is the same as in standard case. So if we have any, we should say that this is an ideal. If we take any element and multiply by something, if we multiply to the right, then since we already have something on the left here, it will remains. If we multiply on the left, then this part remains. So nothing to. The proof is straightforward. Here, of course, here I actually use this subspace of weight zeros, so we have both something on the left and something on the right. After this preparation, let us compute so this is a apply Harish-Chandra homomorphism to this LV. Just do hear me? Is everything okay? So this is final computation of this part. So now I want to combine what I did all the time before. I compute LV using the formula for universal matrix, this formula, and take the projection. And the idea is the following: so using projection, I will ignore this part and this part. So actually, I will use only this. So okay, is it clear what I'm doing? So I will say the computation in more detail, but currently, is it clear? Are there any questions? Can you hear me? Okay, Vanya can hear. Okay, there's no. As I said, now we do this computation. This computation. So we take HQ, trace V, rho V tensor identity. All this applied to universal matrix. Now we substitute the triangle decomposition for universal matrix. How do I write it? On the appendices R plus, R0, R minus. And so actually here I should say that why I'm sure that I can apply HQ, that I indeed obtain the element of the zero weight. This is because of the trace. So if I have trace, then I should apply shift by my constant G, the same by zero weight. So if I have zero weight on the first factor, then I should have definitely zero weight on the second factor. So this is well defined. And this HQ actually kills this R minus and R plus parts. This HQ is a quotient by these things, which comes to H plus and H minus. So this is equal to trace V, rho V tensor identity of R0. This is equal. Now we recall that V is a direct sum of some L weight subspaces. Some subspaces which consist of eigenvectors with respect to this Heisenberg. So we get summation over this function phi, dimension of this V phi. And probably I can even now write the formula which you expect. So we have product for I1 to R, product over S, yi of S, product over S, yi of BS inverse, where this, I want to make it visible, so I'm changing color, where this yi of A is the exponent over Q minus Q inverse H I tilde of minus M AQ inverse power M. So I take the formula for this R0. Let me copy it here. I take this formula. we use this formula for 0. And also we use a formula for this eigenvalues. So we use these two formulas. So replace this HIM by this eigenvalue. We have very nice cancellation. And this. So the final word that Q character is the Harris-Chandra homomorphism applied to the integrable system, which we had to this XXZ operators T. Are there any questions? This is Q. So in terms of, let me say the remark. So we have, in terms of integrable system, we have difficulty XXZ integrable system. And we replace it to more simpler integrable systems. So I don't know how it's called in the. So in some sense, you can think that you replace periodic boundary conditions to the fixed boundary conditions. To the okay, let me say open. Okay, instead of periodic, let me say, okay, periodic to open. And situation becomes more simple. Spectrum of the XXZ integrable system, so this TV, it's this difficult thing. It's governed by Bethe equations, but the spectrum, the Q characters, which govern the spectrum of the psi plus, psi minus, they are much more simple. Usually the Q characters of the representation can be found explicitly. So, you know. Okay. Still no questions, yes? Okay, so there is one more remark or topic which I plan to cover in the course. There's one more topic which I plan to cover in the course. Since this is the last lecture, everybody tired. So I just touch it today, and I hope that to write more in my notes. And this is topic about TQ relations. And this topic is motivated by two observations. So first, some motivation. A is we know that highest weight of the finite dimensional representation is the following function: phi is equal q minus L, p of z, p of q inverse z. This is quite special rational function. Let me check that I didn't confuse my notations, but I think, or rather hope that, yes, looks like here should be q in positive. The question is, what for other rational functions phi? Motivation B is not so naive, so it uses some black box, namely Baxter Relations. So Baxter observed that there is that TV of U that let's for G equals L2, V is standard representations, then TV of U is equal to some A of U. Okay, let me write this a bit clear. Is equal to Q of U times Q of U squared plus and Q of U is polynomial in any finite dimensional representation W. So we have element of the Baxter algebra, TV of U, which is governor for C2. This element is such representations, evaluation representation generates a growth and decreasing. So just if we diagonalize the corresponding operator in any quantum space W, then we are done. But Baxter noticed and used in the proof that actually the spectrum of these operators follows from the spectrum of some other operator, which is simply in the sense that it is polynomial. And the roots of this polynomial are actually Bethe roots. So if we take any eigenvector of this Q, then its eigenvalue is some polynomial, and roots of this polynomial are Bethe roots of the corresponding eigenvector. And so Baxter noticed this is as a relation that in terms of the integrable system, the operator which commutes in some quantum space, And the question is, representation theoretic meaning. Of Q. I use the word correlation in the, maybe it's not a good word for good title of this part, I will think, but anyways, this Baxter relation is called TQ relation or Baxter TQ relation. This is about this relation. Okay. And let me consider and show you an example. So assume that we want that this function phi of z is equal, for example, 1 minus a z inverse. So this is not rational functions. This is not as we used here. So the number of usually we assume that number of roots and zeros for the function are the same and they're related somehow, but this is not. Now this is more simple, but do not satisfy the infinite conditions. And probably you understand in this example, but let me write this is all hostile to. We immediately came to the problem that it is impossible to expect that psi minus of z on the highest weight vector psi is equal to phi of z on psi. Because psi minus of z is a power series in z near 0, and this function does not have such expansion. Okay, this is a problem, and a way to resolve which we will use is actually to forbid this element to act on this space. So we want representations where we do not have this psi minus, so h is negative power, and this is. But we want to have a representation of subalgebra, so we want the representation of uq of b plus. So this will be representation of not whole quantum group, but only of its Borel subalgebra. This is not bad from the point of view of second motivations. So this is sufficient to, because even if we have a representation of B plus, we can define TV, where it is defined here, because this row, its first component belongs to B plus, so we can multiply it by rho V and take the trace. In print, of course, you will see below that the representation becomes n-dimensional, and we have to do some twisting and to do some work to take the test. But in principle, to have a representation B plus is not bad, and this is why our choice is natural. Okay, we want representation of EQ B plus. Now let's try to reconstruct it. So we have. So we have highest weight vector psi. So we assume that psi plus on psi is equal to this function y minus a zim inverse on psi. What is the consequence? And it means that K1 from which psi plus starts on this vector psi is equal to psi. First Heisenberg operator H1 on psi is equal to the following number minus A over Q minus Q inverse psi. And all others high HR of psi is equal to 0, since we have only finite on the one term. This was impossible for if we have representation. I mean, it's not this. We don't have such story for representation of the UQ of G, because this vanishing means that means a lot of other vanishings that you will see here. It will work. Okay, this action of the highest weight vector. Now let us act on its descendant. So assume that we have a vector, say psi prime, which will be equal to E0 psi. This first L highest weight vector, of course, means that I assume that all E alpha plus N delta on psi equal to 0. Now I act by E0, obtain some vector, and E1 E0 on psi is equal to what? Is equal to U squared minus because E1 annihilate psi, and this is equal to, this is minus Q inverse H1 on psi. So it is some number a cubed minus 2. I hope I wrote it correctly. On psi. But if I plan to act by any other element of the sort, so for example, E alpha plus, I act by E alpha plus N delta on psi prime for N greater than 0. Then arguing like this, I obtain action of Hn for Hn plus 1, which is 0, as we had here. Oh, maybe too consistent action. I should write here R. Therefore, this is 0. And so, okay, so this is 0. Now let me make one more conclusion, and then I will come to the answer and write down it explicitly. On the other hand, we know that for all this for R greater than 0. Now, corollary from this will be the following computation. So we have that I alpha plus R delta on psi prime is equal to something like to R over R. And the commutator of the HR. Yes, I think I'm right, correct. Of the E alpha. Xi prime. So this is some number. And now we get two terms. And for R greater than 1, this term vanishes. Because we know that IH, which is greater than 1, vanishes the highest weight vector. Therefore, for R greater than 1, this term also should vanish. Because we know that this is 0. And E alpha act by some non-zero constant, which we computed here. So hence, HR on Xi prime equal to 0 for R greater than 1. And arguing like this, it is easy to see or to guess then HR for R greater than 1 vanishes on whole representation. So actually, this representation of just B plus part of the quantum group, but this representation has huge kernel. Okay, now let me give it as a definition. So we define the representation, which I denote by L plus. So this is a representation, or maybe to say that's called proposition. So, and it says that algebra UQ of B plus has the following representation. L plus of A, which is where the representation space is defined with the space of polynomials, and the action where the action is given as follows. So E0 maps to X, E1 maps to operator X dagger, and we assume that the following commutation formula between X and X dagger. This Q commutator is equal to the value of H1. And everything else can be just computed. What we have to check in order to prove this proposition? We have to check relations from E0 and E1. So we have to check, and also maybe I should write that I assume that K1 on the 1 is equal to Q. It's equal to 1, sorry. The highest weight vector, we have action of K1 is equal to 1 as we had here. This representation has the following names. Okay, before the proof, this is remark. This could be called, sometimes called pre-fundamental. Or oscillatory representations. The origin name is, I hope it's clear. So it's called oscillatory because these separators X and X dagger are some sort of Q oscillators. And fundamental because it has L highest weight, which is given by, so for fundamental representations, L highest weight is given by ratio of two such functions. Have one factor numerator and one denominator. And this is even more fundamental than fundamental representations. So this is why it's called prefundamental. And for the proof, the only thing which we actually have to check is serial relations. Between this X and X dagger. And this is straightforward. And maybe we won't do it now. I believe you're already tired with calculations. Corollary. In this representation, which we constructed, L plus of A, E alpha plus R delta goes to 0 for R greater than 0. And similarly, E minus alpha plus R plus 1 delta goes to 0. And of course, similar for HR plus 1. Indeed, all these elements are obtained from by commuting E alpha and H1. But H1, as we see from this formula, goes to constant. Hence, commuting with this, we get 0. So we get this, and these H's are Q-square commutators of such elements. So they are also 0. So in this sense, it's quite special representation. Okay, are there any questions? Okay, no questions, so I assume that everybody tired. So I just say in words what happens in general. In general, for any I from 1 to R and I star exists unique representation of QQB plus, which is denoted by L plus of A with L highest weight, phi I of Z is equal phi, sorry, where am I? Is equal delta Ij times 1 minus Z inverse A. This is as simple L highest weight as possible. So this is just a rational function, but we have tuple of rational functions only. But in this tuple, only one rational function is not 0, is not 1, and this rational function has just one root, polynomial of degree 1. This is, let me say A. Let me say B, and B is the same. But I write here minus, and here write -1. So there's, when I said this is this has the simplest, actually there are two choices. We can have one root in numerator and one root in denominator, and both types of fundamental representations is possible, exists, and actual difference between them for SL2 is here. Here I put q squared, but I can put as well q minus 2, and again obtain the representation of equal to hat, and it will be actually another fundamental representation. Okay, what is the use of these representations? We can define qi of A to be TLI plus of A. This belongs to UQ of B minus. So it means that I take universal matrix, substitute on the first factor our representation L plus, and then take the trace. Here actually should be some twist, which I ignore for discussion. So this formula is not literally correct. And the property, then this Qi of A is polynomial in A on any fine dimensional representation W. And now the last D there exist relations in growth anti-group K0 of UQ of B plus modulus, which are which category which leads to TQ relations, which categorify TQ relations. Let me just illustrate the point D by an example. Yes, so we have as usual, so we have G is equal to SL2. We have the following tensor product formulas that Vj of A tensor V1 of, let me think, I think what is A squared this equal in K series, of course, to Vj plus 1 of A squared plus, okay, I'm writing this from my head, so maybe I will make some mistake with shifts and so on, but just ignore this. Okay. Now the representation which I mentioned above, L plus of A, is in quotation mark limit of Vj of A, where j goes to infinity, and A cubed in power j goes to 0. And taking the corresponding limit of this representation, we get the following identity in the growth integral of B plus. So we take L of A, multiply to B1 of AQ squared, and this will be equal to, again, K0 to LA of Q squared plus LA of AQ inverse. And then, so this will lead us to the following relation: Q of UT of U squared and this is TQ relation from which I started. Okay, in principle, I have some time, but this is all actually all what I wanted to say today, at least all what I prepared to say, somehow prepared to say today. So, are there any questions? If no, so I stop YouTube.